Yeah, so thanks everybody for being here. It's a pleasure to present our research work at Nethermind.
Yeah,
Looks like the laser doesn't work on the screen.
Will not work because of the white background.
Okay, okay.
It works on the black.
Whatever. Okay. All right. So yeah, I'll talk about avoiding arithmetization overheads. In reality, I will talk about proof systems over integers and other rings. I'll first motivate the problem, and for this, I'll introduce some notation and terminology that we all know. It will only be 2 lines, I promise. So we work with relations R, which consist of pairs, instances, and witnesses, X and W. And in a SNARK for the relation R, given an instance that's public, the prover convinces the verifier that they know a valid witness for the instance. They exchange some messages, maybe it's non-interactive and they just exchange one message, and so on. That's the introduction. Okay. So usually R, in practice, R consists of algebraic equations over a finite field F. It's just a bunch of polynomial equations. It's a system of polynomial equations where some variables have a public entry. For example, the R1CS relation over F is really just a system of quadratic equations with some with some fixed constants that are the x's. Other examples are air, Plonkish constraints, CCS, and this new type of constraint called M3 from the irreducible team. They are all just systems of equations when you look far enough. Okay, so that's fine. When we have proof systems for R1CS over a field, they work nice. But what if we want to prove a claim about a relation that has nothing to do with an R1CS over this finite field? So say that we want to prove CPU operations, which is kind of it's quite a hot topic these days with the ZKVMs. Say we want to prove addition and multiplication modulo 2 to the 64, exclusive OR of bit strings, and so on. So what is done in practice right now is you take your instance witness pair in the relation you care about, R0, and you rewrite it as a new instance witness pair in the relation you know how to work with, the R1CS relation over the field. And we call this, in this work, we call this process arithmetization. The arithmetization is a word that has different meanings depending on where you read, but that's the meaning we give it. So this is fine in theory, on paper, and that's what is being done today in practice as well. But the issue is that it can create a big blowouts, and I'm going to justify this in the next slides. So just a first example is there's this in this paper, the paper claims that ECDSA signature verification, if you prove it over a non-native field, and say M31, the R1CS system has 2 to the 21 constraints versus 2 to the 16 constraints if you work over the native field. So our thesis at Nethermind is that there's room for improvements here, and we believe that there's a lot to be gained. So orders of magnitude to be gained in this direction. We believe that this process, the process of avoiding overheads when you write what you want to prove as polynomial equations, we think it hasn't been researched too much, and that's what we are focusing on. So some examples of computations we want to prove, but we're writing those computations over a finite prime field. A prime field is tricky and produces big overheads. It's computations that involve rationals, fixed point arithmetic, floating point arithmetic, which are relevant for machine learning, finance, FHE. Some FHE schemes use rational numbers. Multiplication modulo powers of 2, relevant for CPU operations, ZKVMs, lattice-based cryptography. Multiplication modulo the product of 2 primes, relevant for RSA cryptography. Multiplication modulo non-native prime, so you want to work over M31, but you want to prove something of a different field. That's also relevant. This comes up in folding, for example. bitwise operations, exclusive or, not, bitwise and so on. Relevant for classic hashes, SHA-256, Keccak. SHA-256 and Keccak are a bit painful to prove today, and also legacy cryptography, AES encryption, and lattice operations for lattice-based cryptography, and combinations of above. If you want to prove, if you want to build a ZKVM, you'll be proving multiplication mod 2 to the n. You will have bitwise operations, and you will likely also have hashes somewhere, classic hashes somewhere. And just to give you an idea of the headaches that arithmetizing on that complicated arithmetizations can bring to the table. So say we want to prove x multiplied by y equals z modulo 2 to the 32 over a field f. So as I said, we can always write some equations that will guarantee that x times y equals z modulo 2 to the 32 over any field. But how does this actually work? Let's look at an example. First of all, I'll start with benchmarks. So Venus is this proof system that works over fields of characteristic 2, and they have these benchmarks where they show that they prove 1,000,000 multiplications over this field. So multiplications of this field, not multiplications mod 2 to the 32, in 80 milliseconds, and then they prove 1,000,000 multiplications modulo 2 to the 32 in 2 seconds, which is more than 20x the native multiplications of the field. So I'm not saying this is how Venus does it, but this is the typical way you would prove x times y equals z over a 32-bit field. You decompose x and y into chunks of small bits. So you decompose x into 4 chunks, each of 8 bits. So you write these equations, and then you put these constraints in here to make sure that the chunks, xi and yi, which are sometimes called limbs, that they belong to the correct range, so that they are not too large. So this guarantees that the decomposition is done correctly. So now you have some lookups or some range checks and linear equations. Now you rewrite the product as a product of the multiplication of the limbs, of the chunks. And now you have to multiply the chunks. And to multiply the chunks, you can either use lookups, for example, in Lasso, or you can use degree 2 constraints, polynomials of degree 2. So if you do it naively, you have 16 chunks, so you have 16 multiplications, plus 8 range checks and these linear equations. If you do it naively, you can reduce the number of multiplications of chunks using Karatsuba and slightly fancy multiplication algorithms. And then you have to combine the multiplication of the chunks into the final result of the multiplication, which requires addition and scalar multiplication, which happens modulo 2 to the 32. And addition and scalar multiplication modulo 2 to the 32 is, again, not native to the field. So again, you have to do tricks to do this final combination. So I'm not going to continue. I will not torture you more. I hope I conveyed the idea of the mental energy and the possible errors you can fall into when you are arithmetizing over the wrong place. So this also points to the fact that if you work on non-native spaces, you also increase the engineering effort a lot, because this takes a long time. If you were just proving statements modulo 2 to the 32, you would just write xy equals z and call it a day. But because you work over a 32-bit field, you have to do all these things. You have to make sure that you do them correctly, because if you don't do them correctly, what you are proving is bogus. Then this translates to audits and formal verification costs and so on, besides proving and proof size cost and so on. Okay, I'll skip this slide, otherwise I'll spend all the talk motivating the problem. This is our table of computations of interests, and practically using usable proof systems today for these computations that are hash-based. In this talk, we focus on hash-based proof systems. I'll say more about this later. So there's bnews can handle many bitwise operations. It cannot handle all of them. It cannot handle AND really natively. And then for lattices, there's dedicated SNARKs that are hash-based and seem to be fast. And yeah, I want to talk a bit about bnews. So as I said, bnews is a proof system that works on binary fields, and there's many bitwise operations that can be easily represented in binary fields. For example, addition of polynomials in binary fields, it corresponds to exclusive OR, because elements of a binary field are polynomials with binary coefficients, and addition of two polynomials there, of two elements in the binary field, corresponds to doing the exclusive OR of each coefficient. And from that, you can build NOT and some other bitwise operations. And this allows, I think this is why bnews is so fast in, for example, proving classic hashes, because many of the operations that occur in classic hashes are native in bnews. There's probably other reasons related to paper bit costs that bnews enables, but that's one of the reasons that they are sort of, that classic hashes are sort of native to the field they work with. And this is witnessed by these benchmarks in here that I put together. Okay, so our ultimate goal at Nethermind is to design a proof system that has what we call a universal arithmetization, which means that all the computations in this table should be native. And we want it to be similar to state-of-the-art proof systems. What's a state-of-the-art proof system? That's a bit subjective, but for now we have decided to take as role models proof systems that eventually run on finite fields, that use error-correcting codes, hash functions, and we take as role model SNARKs, Plonky, Ligero, things like that. Code-based proof systems. We are not like we are not married to these proof systems. We might change them, but that's the role models we take for now. And as a first step, and in this talk, we have limited ourselves to building a proof system that's native for Z mod n for any n. So if n is not prime, then Z mod n is not a field. Just to clarify. Integers and rationals, or any combination of the above, any combination of these at the same time. This, if you can build a proof system for these structures, you get the first 4 rows of this table. Okay, and we are currently building a scheme for everything. I'll also explain a bit how we are trying to do that. Okay, so yeah, our scheme for this Z mod n, Z and Q is called Zinc. And you might think, okay, we have good proof systems. If we have good proof systems for all the rows except the last one, we can sort of just combine them and create proof systems for computations that use all the computations, maybe. For example, zkVM instructions use different computations from the table. Applications like zkID related applications where you do a classic hash of something and then you sign it. A is encryption, TLS. But it's not that easy because there's a lot of interleaved operations between different types of operations here. And that's why, so as a work in progress, so as I said, we are extending our scheme so that we can handle all of these operations at the same time. Okay, I also have comments about Ethereum blocks, but I think I'll skip them. Okay, so the scheme I'm presenting today is a framework. Well, yeah, it's a framework or family of 6 succinct arguments or a collection of ideas for building SNARKs, where Z mod n for any n, Z and Q, so polynomial equations over these rings, are native. And we can also handle different constraints over many of these rings in the same proof. We instantiated the ideas with Spartan and PCS that looks like Ligero or breakdown. And when the scheme runs, it's just the way we instantiated it is like Spartan compiled with Ligero or breakdown, run modulo and random prime. We could instantiate it with different schemes, but that's the one we choose. But it's not there's not much that forces us to use Spartan and Ligero. We could likely use other schemes. So one feature of the scheme is that for running purposes, it just looks like Spartan plus Ligero run modulo random prime, basically. But then, theoretically, when you want to prove its security and so on, there's a lot of nuance in there. So when it runs, it looks simple, but then the security proofs are, in my opinion, are quite nuanced. So we are implementing the scheme. It's a work in progress implementation. We have these preliminary benchmarks, for example, to commit to a polynomial of 20 variables, multilinear polynomial of 20 variables. It takes us 10 milliseconds with the coefficients of the polynomial having 32 bits. I think the 10 milliseconds is similar to other times that it takes, so to other schemes that are hash-based, like breakdown. I think breakdown takes approximately this time in many reports, but breakdown over a fixed finite field. Here I'm talking about PCSs for possibly witnesses with coefficients in these rings. Creating an opening proofs right now takes us 35 milliseconds, but I think that we will bring this to less than 10 milliseconds because on paper, opening proofs of breakdown should be cheaper than committing. So as I said, it's a work in progress implementation. So, but anyway, these numbers mean that there's essentially no overhead for Zinc compared to its finite field counterpart. But on the other hand, Zinc can handle constraints in these rings, which means that Zinc is likely to work with much smaller circuits than the counterparts. So for the same witness size, performance is very similar, but Zinc will likely work with much smaller witnesses in some applications. And yeah, I mentioned that Zinc runs modulo random prime. If you are wondering if there's a lot of difference between running modulo a prime that's not known at compile time and a prime that's known at compile time, there's not that much difference, at least when the prime has 128 bits, which is the size of the prime we use. And then conceptually, this doesn't come up in the actual proof system when you use it, but conceptually, we introduce this new primitive called, yeah?
Just to clarify, this would be for like a random prime known at compile time versus not at compile time. Not for, I guess it would be an advantage having like a special purpose prime that's sort of particularly selected for efficiency.
Here we compared with the Stark prime, so the fixed prime of the Stark proof system when they were using a large prime. And we didn't see difference. Maybe if, we are not going to work with 32-bit primes in our modulos because of soundness reasons, but if we make this comparison with M31, then probably there would be a difference because M31 has certain advantages, right? Okay, so let's see how I'll try to explain the main ideas of how this works. Let's forget everything. about rings and integers and rationals. And let's just try to build a proof system for R1CS constraint modulo n, for any n. So we want to build a proof system for this thing. So we have here we have the usual Hadamard product of matrix vector multiplications, which is supposed to equal another matrix vector multiplication. And this Z is the concatenation of the public instance and the witness. And an initial observation is that things are equal in Zn. Things are equal modulo n, even only if they are equal as integers after you add a multiple of n. So this R1CS constraint holds modulo n, even only if there exists some vector such that the R1CS constraint holds after you add a multiple of a vector that's a multiple of n. So instead of proving the R1CS constraints modulo n, you might just go to the integers, if you like the integers for some reason, and prove this constraint adding this extra witness here. So if there's you add an extra witness and prove this thing over the integers. And if you prove this, then you have proved this. So because of several reasons, it's pretty hard to build a proof system over Z mod 2 to the n. And it doesn't look like it's that hard to build a proof system over Z at first glance. So we can decide to work over the integers and build a proof system for this relation. It's just the same as before, but now everything are integers, and we added this extra term. And note that if in here we put the Hadamard product of u and some public vector, then suddenly all the constraints in this equation, each constraint encodes a constraint modulo a different number. So if the first entry of n is 2 to the 32, then the first equation of this R1CS encodes a constraint modulo 2 to the 32. If the next n is a prime, then the second equation of this constraint encodes an equation modulo that prime, and so on. So we have modular constraints for many moduli in the same relation. For technical reasons, we have to ask that the witnesses and instances have a bounded bit size. This bit size we have to put some bound. That's a technicality, but it's going to be 256 bits, for example, in practice. OK, so we want to build a proof system for integers, for these constraints. So we might just try to follow the PIOP plus PCS approach that we all know and love, which is you first build a PIOP for your relation with soundness holding against provers that send polynomials with polynomials of the correct form. That's what you do in SNARKs over a field. You do a PIOP. So you build a proof system that works if you assume that the prover sends you polynomials with coefficients in that field. So we assume the same and build a PIOP for this. That's the idea. And then we design a polynomial commitment scheme that guarantees that the prover is using these polynomials. OK, and then we compile it with standard compiler arguments. I'm not saying we do this. That's the first idea you might come up with. So there are several issues. So an issue with the first approach is that Spartan for integers is not too difficult to build. It's if you try the obvious things, they work. The problem is the performance. So there's some checks. The verifier will be sending 128-bit challenges, and then you will start multiplying them in the sum checks. And your integers will start growing, and you will end up working with integers that have thousands of bits. So in terms of performance, it's not clear that idea number 1 is very reasonable. And idea number 2 is easier said than done. So there were not, as far as we know, there's no PCSs for integers that are very fast, that are comparable to state-of-the-art PCSs from today. The existing ones are based on groups of unknown order, and they are very slow. I try to estimate the running time, and I won't say, but it's not good. And yeah, okay. So how can we address these issues? So there's this paper from last year by Campanelli and Hal Andersen, where they propose sampling a random prime queue and then running the PIOP modulo random prime. If you run the PIOP modulo a prime, then you don't have the issue of your integers blowing out of size. And the randomness, if you guarantee that the prover is sending polynomials with coefficients of at most b bits, then the randomness guarantees that running modulo a prime stays sound. Now, regarding 2, so we want to use this trick. We're going to use the trick of Campanelli and Hal Andersen. Now, 2, as I said, it seems to the issue with building PCSs for polynomials over Z is that it is difficult to extract the integer polynomial. So it's not that difficult to extract some rational polynomial of some, if you don't care about the size of the coefficients. So if you've written a knowledge soundness proof, you probably have ended up writing a system of equations that the extractor is supposed to solve. And the solution is the witness, the extracted witness. So when you solve a system of equations, if you are not in a field, you are in trouble, because usually you have to divide by some numbers. And if you are not in a field, you cannot do it. If you are on a field, then it's fine. The extractor just solves the system of linear equations. If you are in a domain, which is contained in a field, you might just want to extract the witness over the field of fractions, which is what's happening here. So if you, for example, try to do breakdown over integers, and then you want to prove knowledge soundness, the extractor cannot extract an integer polynomial. It extracts a rational polynomial, because it has to solve a system of linear equations. So what we decided to do is to work over rationals instead of integers. This makes extraction reasonable. It's doable. You have to guarantee that there's a certain bound on the coefficients, which makes things trickier, but it's doable if you go to rationals. So we designed this PCS, which is called ZIP. It's based on Ligero breakdown PCS, which is a PCS for polynomials with coefficients over the rationals of certain bit size. This allows us to compile our relations into a SNARK, but our relations now are relations over rationals, because we can only guarantee that the prover is using rational numbers. I started with the R1CS and so on, but all this really works for any relation that can be described with polynomial equations. So we have a SNARK for any relation that is polynomial equations over rationals. In particular, we have lookups over rationals, because lookups can be expressed with polynomial equations. It's not completely obvious if you haven't seen it, but you can do it. So we have lookups for rationals. So we can enforce that the witness is integer by using a lookup in Q. So we can combine an R1CS constraint over Q with a lookup over Q to guarantee that the witness is an integer. And this lookup also happens modulo random prime. Everything happens modulo random prime. Okay, I think I'm out of time, right?
5 more minutes.
5 more minutes? Okay, I'll skip this because this is just a summary of what I just explained. And I'll explain next steps. So as I mentioned, Zinc allows to work with any modulus, equations of modulo any modulus, integers and rationals. But we want other operations, right? We also want, for example, bitwise operations. And we cannot really encode bitwise operations currently in Z, Z mod n, and so on. So what are we working with? So remember the first step, we transform this R1CS modulo n into this kind of looking R1CS constraint over the integers. And now remember that bitwise operations is basically addition on binary fields. You can represent exclusive OR as addition in binary fields. And now let's remember from abstract algebra that a binary field is the quotient of the ring of polynomials with integer coefficients with the ideal generated by 2 and some polynomial of degree n, n plus 1, or n. Okay, and the elements of this binary field are represented as polynomials of degree. As I said, it's the set of polynomials of degree less than n. So if we want to prove a constraint over a binary field, we could instead lift it to Zx with a similar idea as what we did for Z mod n. Instead of proving that the R1CS constraint holds over the binary field, we could prove that something like this holds over the ring Zx. And this is just the initial R1CS constraint, and then there's a vector that's a multiple of 2, and a vector that's a multiple of this irreducible polynomial. So we add these two extra witness vectors, and maybe we can prove something here. We can prove this constraint here. And if you think about it, everything that we want to prove happens on Zx, on a projection of Zx into some ring or field. Like binary fields are projections of Zx. Is the quotient of Zx by an ideal. Cyclotomic rings are quotients of Zx modulo an ideal. Prime field is a quotient of Zx. Z mod n is a quotient of Zx, and so on. The only operation that we cannot really model this way is the bitwise AND. From all the operations of interest I mentioned, bitwise AND is a bit tricky, but you can do tricks anyway. And yeah, so if you can build an efficient proof system for polynomial constraints where the polynomials have coefficients on Zx and the solutions are vectors of polynomials, then you get an efficient proof system for all computations, or everything we want to prove. Okay. Thanks.